here, so don't say anything you don't want said on a recording out there. They are posted publicly on YouTube. So, okay. So anyway, that's my contact information if you need to get a hold of me outside of class. We're going to start looking at motor mounting, motor control. Basically, most of what we're going to be doing today for math is going to be motor mounting and electrical. So some of the things we want to talk about are just ratios are going to be the big one. And a ratio is nothing more than a comparison between two numbers, or between two or more numbers. So I might do a comparison. I have two CNC classes right now. One is high schoolers. I just came from the high school class, so this is a nice little switch from dealing with high school kids. I have 11 high school and 8 adult. So if I have a ratio of high school students to adult students, that'd be 11 to 8. Or you might see it with a colon like that, 11 to 8. Now, a lot of times those ratios can be reduced. So if I had, let's say it was 12 high school students instead of 11 high school students, we can reduce this similar to like we do with fractions. Both 12 and 8 can be divided by what number? 2 would work. And 4 would have worked as well. Yeah. 12 divided by 2 is 6. 8 divided by 2 is 4. And yes, we can still divide both of those by 2 again. Get 3 to 2. If we could have divided by 4 to get the 3 to 2 right away. Most of the ratios you're going to work with are going to be simplified like that. In electronics, one of the big ratios you're going to work with is a transformer ratio. So transformer ratios are dealing with the number of turns in the coils. So you have a primary coil and a secondary coil. Your primary coil is where you have your applied voltage or applied current. And of course, your secondary coil is where you're going to have an output voltage and current. There's also a core in most transformers. There can either be a shared core or whatever. The efficiency and stuff depends on the material in the core, but we're going to be concerned with just the math of the coils. So let's say we have 800 turns on the primary coil. All that means is literally 800 wraps or 800 circles made by that wire wrapped around whatever core it's being put around. And let's say we have 200 turns on the secondary coil. It's going to be a step down, yes. So your ratio is always going to be the number of turns on the secondary coil versus the number of turns on the primary coil. So it's going to be 200 over 800. Or a 1 to 4 or 4 to 1. You got it. We're going to look more at the transformers and stuff as we go through stuff. Other ratios that are important that don't look necessarily like ratios. Threads per inch. And technically threads per inch is not a ratio, it's a rate because it's comparing two things with different units. A ratio up here is comparing coils to coils that have the same label. A ratio, threads per inch, is comparing the number of threads to the number of inches. Let's say we have 28 TPI, threads per inch. The ratio of threads can be used, or the rate of the threads can be used to create a distance using proportions. So 28 threads per inch is really saying 28 threads in 1 inch. So that is a rate rather than a ratio. But let's say we need to advance a nut onto that bolt a distance of 1/4 inch. This setup where we have two ratios or two rates that are set equal to each other is called a proportion. And when we deal with any sort of rates and ratios, which is a lot of electricity, proportions are a very powerful tool. To find the missing number in a proportion, the easiest process or the main process is called cross, multiply, and divide. And so what that is we have numbers that are at angles or diagonals to each other. Those two numbers are diagonal. So we would take the 28 threads times the 1/4 inch is going to give us 7. These two numbers also have to multiply to make the same thing. Now, if we're thinking with basic algebra, if we called that x, that would be 1 times x also has to equal 7. You would solve that equation by dividing by 1, which x equals 7. To shorten that process up without having to use the equation and solving the equation, like we said, we just do cross, multiply, and divide. We multiply the two numbers that are diagonal to each other, the 28 and the 1/4, and then we just divide by the number that's diagonal with our missing number, the 1. So what this is telling us is we have to advance that nut 7 threads to get a 1/4 inch, or 7 complete turns onto that bolt to get a 1/4 inch. So if I have 20 TPI and I turn it, let's say we're going to go 15 turns. How far do I advance up that bolt? 3/4 of an inch. Very good. 20 TPI is 20 threads per 1 inch. 15 turns is the same as saying 15 threads. That's going to give us our inches. So what numbers do we multiply here? 1 times 15, and then we divide by the 20. That does come out to be 0.75 or 3/4 of an inch. Simple enough? So why am I going through this? Well, when you're mounting motors, adjusting the motor is a big deal. If you have an adjustable motor mount, a lot of times you're just turning a nut onto a bolt to adjust the alignment of that motor. So it's very common to have a motor where you know that your mount is on a bolt that's 24 threads per inch, and you need to go 1/8 of an inch of adjustment. And so you need to figure out how far do you have to turn that. So 24 threads is 1 inch. I need an 1/8 inch. What gets multiplied? 24 times 1/8. You got it. Then, of course, divided by the 1, which divided by 1 doesn't do anything, so we don't really have to do it. 24 times 1/8 divided by 1 will be 3. So we have to turn the nut 3 turns. That'll give us our 1/8 of an inch of adjustment. Any questions on anything I've done so far? Anybody have questions on multiplying the whole number in a fraction? Everybody's good with that? So as I mentioned, this is all about alignment. There are a lot of different things that can be done for alignment. Have you guys talked about anything with alignments yet? Angular alignment, parallel alignments, any of that stuff? In the past? Okay.
It was day one.
I guess, yeah. You only had 2 hours, so probably not a whole lot to bring in. So one of your things with alignments, Parallel alignment is pretty easy to deal with. Parallel alignment, you're aligning two shafts that are parallel, just not aligned. So all you have to do is lift or lower one shaft to get it there. Usually you're lifting the motor to line it up with the other shafts. The shaft that's on your machine is usually fixed because your machine is usually the larger component. So you're raising the motor to match it. If you have an adjustable motor mount, you either have an adjustable mount where you can raise it with turning the bolts, or you have to shim it. Go ahead. Okay. Angular alignment is where they're not parallel. So we have to adjust. Hopefully the machine is parallel, or the machine is level to the ground, and you just have to adjust the motor to be parallel to that shaft. Two different possible conditions. We're going to deal with the easier of the two. We're going to deal with the machine is always either going to be level to the ground, or that's going to be what we're going off. We're going to be parallel to the machine. Even though the machine is not level, you're going to align the motor shaft to it. And let's say we have pardon my artwork. I'm a math teacher, not an artist. So we have a motor that's set up something like this. It's out of alignment, and we need to raise the end of the shaft. Which foot I'm going to call this the near and the far foot. Which foot has to be shimmed, the near foot or the far foot? Near foot. So shimming the near foot is going to raise the shaft. Well, there's a lot of distances that can be used as ratios here. One of them is the distance between feet. Let's just say that we have 8 inches there for now. When we're looking at raising that end of the shaft, the other distance we're looking at is from the end of the shaft back to that far foot. Let's say that's 20 inches in this situation. The ratio between the shim and how far that shaft moves is going to be equivalent to this ratio of lengths. So if I shim that foot 0.010 of an inch, it is working on an 8-inch, called a moment arm, an 8-inch arm to that far foot. The amount it's going to raise the end of the shaft is going to be quite a bit more than that 0.010 of an inch, because it is working on a longer arm of rotation or moment arm. That's 20 inches there. How do I find this missing number? What two numbers multiply? There you go. 0.01 times 20 and then divided by the 8. 8 is diagonal with our missing number, so we divide by it. So 0.01 times 20 divided by 8, we get 0.025. So the 10,000 shim will raise the end of the shaft 25,000ths of an inch. So let's say that we do some measuring here, and we realize that we need to raise the end of the shaft 40 thousandths. We set up the same ratio, so the ratio is going to be the shim over the distance between feet is going to equal, we'll just say the raise over the far foot to end of shaft. So it's the same formula we had up there, just written out in words. Do we know the shim? We don't know the shim, yes. We know the between feet was the 8 inches. Do we know how far we have to raise it? The 40 thousandths. You got it, 0.04. And the far foot to the end of shaft is the 20. What do we multiply? There you go. The 0.04 times the 8, and then the 20 is diagonal to the missing numbers, so we divide by 20. Giving us 16 thousandths. That's what we need for a shim. Any questions? So I'm going to give you one to try. So the distance between feet here is going to be 10 inches. End of shaft to far foot is going to be 18 inches. We need to raise the end of the shaft. $54 thousandths of an inch. Find my shim. So if we set this up, we're looking for the shim, right? So put X, perfect, over what? 10, and then on the other side? Over 18, perfect. So we're going to multiply 10 times 0.054 divided by 18 gives us what? 0.03, there we go. So we need a 30 thousandths shim. Any questions on that? So this is shimming the front foot. For that to work, it's assuming that the end of the shaft is below the machine shaft, and we have to raise it up. But what if we need to align it by changing the rear foot? What if our alignment looks like this? I mean, sometimes we can remove shims from the front foot if they're there, but sometimes we have to shim up that rear foot to lift it up. It'll still bring down the end of the shaft. So we have our distance between feet here. I'm going to put in 8 inches again. Our distance to the end of the shaft, we're just going to go 18 inches. Let's say I need to, well, let's just do this. Let's put in a shim here of 10 thousandths again, 0.01. What does it do to the other end? Well, here up here, we were pivoting on this rear foot. That rear foot stayed stationary. That's why all of our distances were measured from it. The distance between feet and the distance to the end of the shaft. Here, what's our pivot? The front foot, the near foot. We're pivoting there. So the 8 inches between feet is relevant. The 18 is not. The distance we need is the distance from that pivot or the front foot to the end of the shaft, which is going to be 10 inches. Good. So now the movement there, we have our shim over the distance between feet is going to equal our drop over the near foot to the end of the shaft. So we have our shim of 10 thousandths over what's the distance between feet? 8 inches. Good. We don't know our drop. That's what we're going to find. What's our distance from the near foot to the end of shaft? 10. So we'll multiply there. Perfect. 0.01 times 10 divided by 8. Going to give us 0.0125. So you'd end up shimming at either 12 thousandths or 13 thousandths. I don't think any of you have a half a thousandth shim anywhere, do you? I know I do some of the mechatronics stuff. In the mechatronics lab, I think we have 2,000 shims, and those get pretty, it's like running, aluminum foil underneath the thing. So if I give you a distance between feet here of 10 inches, front foot to end of shaft of 16 inches, and we need to lower the end of the shaft by let's say 52 thousandths of an inch. So we're going to use that same ratio. Do we know the shim? No, that's what we're trying to find here. What number goes below here? The 10. Now, if you don't remember the formula, the way to remember is to find the pivot. This is the foot that stays stationary, so that's where we're pivoting. The shim goes here, so the distance from the pivot to the shim is the 10 inches. Over here, we know how far we need to drop the shaft is the 0.052 inches. What number goes below it? Careful. 16. So here's our pivot. The end of the shaft is right here, so that distance is 16. Yeah, it gets confusing which one's which. Yep. Oh, sure. Gotcha. So what numbers get multiplied here? So 0.052 times 10 divided by 16. This one's going to be ugly. Not so bad. 0.0325 inches. Not so bad? Have you tried one on your own? So with this setup, you need to lower the end of the shaft .40 thousandths of an inch. See what you come up with for the shim. We're shimming the far foot. So when we set this up, do we know the number here? That's the shim. That's what we're looking for, right? That's X. What goes below that? 6. On the other side, do we know what goes on top? The 40 thousandths that we need to drop the shaft. Yep. And on bottom, the 10. Perfect. And so we'll cross multiply and divide. 6 times 0.040 divided by 10 gives us what? 0.0424. So 24 thousandths of an inch shim. Questions? What about angular offset and flanges? This is really going to challenge my artistic ability. So if we have our shafts aligned, we still have to connect them somewhere. One of the devices that we connect them with is a flange. So preferably, those two flanges, once we have them on the shafts, the gap, this is called the gap at 12 o'clock. Just like a clock, it's the gap at the top. This would be the gap at 6 o'clock. In a perfect world, those would be exactly the same. That would be a perfect angular alignment. They're not always going to be that way. So there's an allowable difference on a 10-inch flange. So the 10 inches is just the diameter of the flange from top to bottom. In your industrial mechanics textbook, this table that I'm going to be putting up here is on page 326 of it. And I'm not going to put in the full table. But the table lists speed, excellent alignment, and then acceptable alignment. We're going to be working in the realm of acceptable, because as long as you're at least acceptable, that's all that matters. And so we're looking at G is going to be our actual difference in the gap. So that's between the 12 o'clock and 6 o'clock. D is going to be the actual diameter of the flange. Capital D is 10 inches because the chart we're using is for a 10-inch flange. And then G is the number to compare to the table. So our formula to get capital G to compare to the table is little g times big D over little d. Now in reality, on the calculator, you're just going to type in little g times big D divided by little d. I'm going to keep it pretty simple. I'm going to assume that we've got the flanges set so that they touch either top or bottom, it doesn't matter which, so that whatever the other gap is our little g. We don't have to subtract the gap at 12 and the gap at 6. So if I tell you that that little gap is, what do I have? 4.6 thousandths, 0.0046 inches, and we are running at 1800 RPM. So first thing we have to do is calculate our big G. So we put in the 0.0046 for little g times what goes in for big D? Always 10, just because that's what the table is. If you had a table that was listed for a different size flange, you'd use whatever size the table is listing. Divided by, I didn't give you the actual diameter here yet. Let's say that that is a 4-inch flange. So what goes in there to divide by? 4. So 0.0046 times 10 divided by 4 means that we would have 0.0115. What that is saying is that's what the offset would be if this were a full 10-inch flange. A bigger flange would have a bigger offset on the same angle. So this is the number we need to compare to our table. What line of that, do you guys have that table open? We have it handy. What line of that table do we need to go to? So 1800 RPMs would be between the 1000 and 1999, right? So 0.010. Are we under that? We are not. We're slightly over that. So that is not an acceptable offset for that. No, it's not going to be good, no. Yeah, it'll vibrate itself. It'll work for a while, but it'll vibrate itself into some issues. So let's say we have a shaft operating at 3,200 RPM. Find the maximum acceptable offset for a 6-inch flange. So 3,200 RPM. Go to the table, we find 3,200 goes between what range? You got it, 3,000 and the 39.99. And we're not concerned with the excellent, we're concerned with the acceptable, which is 0.004. So the 0.004 is the big G, that's the acceptable. We need to find the little g. Of course, the table is for 10 inches. That's divided by, we actually have a 6-inch flange. So we now have to solve this for little g. To do that, it's probably easier if you have the fraction calculator to list that as division as a fraction as 10/6. We would get rid of the 10/6 by either dividing by 10/6 or multiplying by the reciprocal of 10/6, which is 6/10. So the reason why that's easier is if we divided 10 divided by 6, we're going to get 1.66666. Still be acceptable as long as you go out to at least 5 or 6 decimal places. But here we can just take the 0.004 times 6 divided by 10 to get 0.0024. If you had divided this out, 10 divided by 6 gives you 1.66667. Go to at least 5 decimal places if you're going to do that. So we would have then, come on. My pen's going crazy on me here. There we go. So we'd have the 0.04 or 004 equals little g times the 1.66667. And then to solve for little g, we would divide out the 1.667. So we should get approximately the same answer. You see, bless you. You can see it's a little bit off because of the rounding in the answer. How do we know that we have to divide by the 1.667 here? Yeah, we have to get rid of it. It is, there you go. It's multiplying G, so to get rid of it, we do the opposite. That's why we have to divide by the 1.667. So let's put this together. On an 8-inch flange, the gap at 12 o'clock is 0.251 inches. The gap at 6 o'clock is 0.248 inches. It's operating at 2,700 RPM. Tell me if that's acceptable. I'll give you a couple minutes. Where would we start on this? Well, we have to get our actual offset, which is subtracting the gap at 12 and the gap at 6. What's the difference there? 3 thousandths. So that is they call it the vertical angular offset. So that is our little g. So we go into our formula, 0.003 times what? The table is set for what diameter flange? 10. Then divided by the actual flange of 8. Good. So 0.003 times 10 divided by 8. We get 0.00375. Yes. The 2,700 is, in the 2,000 to 2,999, 0.005. So we are less than acceptable. So yes, that is an acceptable gap in the flange. Any questions on that? So what if we have to shim our motor to make up for this gap? Well, VA is that angular offset. Technically, it's vertical angular offset. That's where the V comes from. D is the diameter of the flange. And A, distance between the feet on the motor. the shim size, S, is going to equal the vertical angular offset over 2. The reason is we're only dealing with the radius rather than the diameters when we're dealing with this. Divided by the actual diameter over 2. Now, if you're good with your math, you might realize that the 2's are going to divide out. You could actually just do the VA divided by D, and it would work out exactly the same. Times A, which is your distance between your feet. So if I have a gap at 12 o'clock, 0.308 inches, a gap at 6 o'clock, 0.296 inches. First, what is my vertical angular offset going to be? .012, 12 thousandths, perfect. A little bit of an off-topic question, but, well, not off-topic, but not a math question. Which foot do I have to shim, the near foot or the far foot? So the gap is wider on top. I need the rear foot or the far foot has to go up, yes. So that is my vertical angular offset. If I give you a flange diameter, let's see here, let's do 4 inches. And the distance between feet. I have this down here somewhere, 8 inches. How far would I have to shim that? Well, it's the 0.012 over 2 divided by the diameter is 4 over 2 times the 8. Now again, I'm going to shorten this formula for you. These 2's cancel out. So it's really just the 0.012 divided by 4 times 8, which ends up being what? There you go. 24 thousandths, 0.024. Okay, before we go on break, one more topic I want to squeeze in. I want to squeeze in thermal expansion. Then after break, we'll be able to focus strictly on electricity. So thermal expansion is kind of a funny thing. If you deal with really extreme temperatures, it does things way different than what we would think. We're only dealing with the range of temperatures that humans might be able to survive in. Most of your machines are not going to operate a lot above that temperature because the room temperature has to be survivable for the operators. But if like steel, for example, you get up, I believe, somewhere around 930 degrees, steel actually shrinks for a second. And it starts to contract. Well, what happens is the metals have a crystalline structure. The atoms are arranged in a certain structure. Well, when it hits a certain temperature, they rearrange to a more efficient structure, so it actually shrinks. That's why heat treating hardens steel. You get it up above that transformation temperature, they rearrange that more compact arrangement, and then you cool it really quick. That's why you quench it, and it freezes it in that arrangement. It can't get out of that arrangement, so now you have a steel that's more dense and it's more hard. We're not going to, when we're talking thermal expansion, we're talking that we're staying below that transformation temperature. Obviously, you're not going to have too many things operating at 900 degrees because the operator wouldn't be able to stay anywhere near it. So when we're dealing with thermal expansion, we have a piece that's going to start out with a given length. When it expands, the difference between the cold length and the hot length is going to be delta L. Have you guys used that triangle to signal? Yeah, we have before, haven't we? It just means the change in length or change in a value. Delta T means the change in temperature. And C is a thermal coefficient for the material. So the formula is simply the change in the length of the material. Come on. Is equal to the length times the change in temperature times that thermal coefficient. So let's say we have a 9-inch piece of steel at 72 degrees Fahrenheit, heated to 134 degrees Fahrenheit. I will tell you that our thermal coefficient that we're going to use is 0.000009 inches per degree Fahrenheit. Now, a little side note. A lot of textbooks will just list that as 9 times 10 to the negative 6. When you see that, 9 times 10 to the negative 6, what that negative 6 is saying is that 9 is in the 6th decimal place. 1, 2, 3, 4, 5, 6. So to find my delta length, I have my original length of 9 inches times, what's my difference in temperature?
9. Oh, sorry, it's
134 minus 72 is that 62? Times the 0.000009. So about 5 thousandths of an inch. Probably not going to be noticeable on a 9-inch piece of steel, huh? Let's say I have a 630-foot bridge. No, we don't have to. We can do it in feet. So a 630-foot bridge at 68 degrees Fahrenheit. In the sun, can get up to, we're going to say 118 degrees Fahrenheit. We're still going to be with the 0.000009 degrees is our inches per degree Fahrenheit is our thermal coefficient. So our expansion, we can just use the feet here. 630 feet times 118 minus 68 gives us how much? 50 degrees times 0.000009. The difference is, since this was in feet, our answer is going to be in feet. We get 0.2835 feet. Now, if I want to convert that into inches, what do I do? Not divide, times. There we go. 3.4 inches, almost 3.5 inches in length that it gains. Now, you wouldn't think that's noticeable, but on the length of the bridge, that'll buckle it up a couple of feet in the middle. Any questions? Okay, it is break time, so go ahead and take 10 minutes. We'll start up at 10:30 with electricity. Get it going again. So we're moving on to electricity. And this is what it sounds like what you guys have been doing most of the morning. So I'm sure you've probably heard a little mention of Ohm's law. So Ohm's law gets written one of two ways. V equals IR, voltage equals current times resistance, or E equals IR. Does anybody know the difference between the two formulas, why they're different? So V is voltage. Voltage applies to DC current. A battery produces a voltage. A capacitor can store and release a voltage. E is short for EMF. It's electromotive force. It is for AC systems. Technically, an AC system does not produce a voltage, it produces a force. It's a push and a pull. A voltage only pushes, an EMF pushes and pulls. Have you talked at all about AC current yet? So what a DC current would be is if this is 0 volts, you have a voltage level and you're at that voltage level all the time. AC current, yes, starts out at 0, goes to a positive level, and then it'll go down to an equal negative level. It's a sine wave, exactly. When we deal with AC current, by the way, what we're dealing with is our AC voltage, I should say. We're dealing with RMS voltage. 120 volt system, that is not the peak voltage. If people think that this means that means this is 120 volts, it is not. It's 169 or 170 is what it ends up being. Yeah. So Ohm's law, we're going to use, since you guys will mostly be working with, most of your machines will work off AC voltage. Some of your control circuits will work off DC voltage. When I say control circuits, you know what I'm talking about? So your controls that deal with your switching and turning everything on and off, a lot of those are DC voltage, a lower DC voltage, 24 DC volts DC, where the actual motor itself has to run off the 240 or 480 volt AC. So we're going to be sticking with talking mostly about AC, so we're going to use the form E equals IR. Now, I like to just use that formula, plug the numbers in, and solve the equations if I need to, but there are other forms. If I divide by R on both sides and solve for the current, I get the current equals the voltage divided by the resistance, or I get the resistance equals the voltage divided by the current. So if I wanted to find the voltage across a load, if the load resistance is 1800 ohms and draws a current of 0.250 amps. So simply to find the voltage, E, current times resistance. Perfect. 1800 times 0.25, which will give us, what's that, 450? Okay. I'm pretty sure it's 450. Now, the way I listed this is probably not how it would typically be listed. We would probably not list 1800 ohms. Good chance that would be listed as 1.8 kilo ohms. And it would probably not list something smaller than an amp in amps. 0.25 amps would probably be listed as 250 milliamps. Those prefixes, K stands for kilo, which means 1,000 times whatever the number is. M stands for milli, which means 1/1000th of the number. So milliamps would be 250 divided by 1,000. That's the 0.25 amps. Kilo ohms is the 1.8 times 1,000. That's the 1,800 ohms. So we actually define the voltage across a load. If the resistance is 2.4 kilo ohms and the current is 150 milliamps. So in our formula for Ohm's law, E equals IR, the current has to be in just amps and the resistance has to be in ohms. So for amps, the 150 milliamps, how am I going to put that into the formula? 0.15 or 0.150 times 2,400, good, 2,400 ohms. So since this is milli, we have to divide this by 1,000 to put it in. Since this is kilo, we have to multiply that by 1,000 to put it in the formula. And that ends up being, what, 360? So 360 volts. Any questions? So I'm going to ask you to find the current through a 1.6 kilo ohm resistor with a 32 volt voltage drop. So I could still use E equals IR. I'd put the 32 in for the 32, not 23. 32 in for the voltage. I'm looking for the current. 1.6 k ohms would go in as 1,600. And I would solve for I by dividing by the 1,600. But we did have those alternative forms of the formula up there where we said I is equal to the voltage divided by the resistance. So it's probably a little bit simpler if we do use that other form. What goes in for the voltage? 32 volts. And for R again, 1,600. We divide that out. We get 0.02. That is amps. Now I could list that as amps, but it's less than 1 amp, so we would typically list it as milliamps. And the conversion is 1,000, so that's going to be 20 milliamps. So we have 1 amp equals 1,000 milliamps as we're converting back and forth. If I have 0.02 amps, put that over 1, multiply. We're getting rid of amps, so amps has to go on bottom. That's the 1 amp. We're going to milliamps, so milliamps, the 1,000 milliamps goes on top. These are equivalent, so this fraction is what we call a unity fraction. The numerator and the denominator equal each other. You have a question or just stretching? Just stretching? Okay. So it's really equal to 1. So multiplying by it will not change our value. It'll just change the appearance. The amp cross cancels out. 0.02 times 1,000 gives us 20, and the units we have left are milliamps. If we were going the other direction, if I had 350 milliamps and I want to change it to amps, I put it over 1 and I'm going to multiply. Now we have milliamps, so I'm going to put milliamps on bottom to get rid of it. It's 1,000 milliamps equals 1 amp. The milliamps cross cancel out, and now the thousand's on bottom, so we divide by the 1,000. So 0.350 amps. Similar conversion works with our ohms. 1 kiloohm equals 1,000 ohms. So if I give you that we have 2.4 kiloohms, and I need to change that into ohms to put it into our formula, I have kiloohms, so I'm going to put kiloohms on bottom. 1 kiloohm equals 1,000 ohms. So again, the kiloohms cross cancel out. 2.4 times 1,000, since the 1,000's on top, is 2,400 ohms. As you move the decimal place 3 spots, exactly. Yeah, if you're good with your metric system, it's 3 spots over, so you move the decimal 3 spots. So I'm going to have you try this one for me. Find the resistance. So I'm finding resistance. This is going to be R equals voltage divided by current. If 120 volt drop pushes 40 milliamps. So that's just saying there's a 120 volt drop across the component, and there's 40 milliamps flowing through it. So what goes in for E? 120. What's going to go in for I? 0.04. There we go. Which, what does that come out to be? 3,000? Yeah. So that's 3,000 ohms, which, of course, if we change it to kiloohms, would be 3 kiloohms. Sure. Questions on basic Ohm's law? So the next step up from Ohm's law is power law. The power law, the power dissipated or produced in a circuit is the voltage times the current. $120-volt circuit with 200 milliamps flowing. power is just the voltage of 120 times 200 milliamps is going to go in as 0.2. That's a 24 watt circuit. Now this can be written in different forms as well. If I wanted to find the current, that's the power divided by the voltage. We'd ask you to find the current draw of a 60 watt light bulb, assuming obviously that it's operating at 120 volts. Yeah, 60 divided by 120 is 0.5 amps or 500 milliamps. Yeah, exactly. Sometimes we don't have the voltage or we don't have the current, so there are alternative forms of the power law. So power equals voltage times current is the main one. If we don't have the voltage, if we go back up to Ohm's law, we saw that the voltage is equal to I times R. Well, we can put that in for the voltage. Ends up being I squared times R. If we don't have the current, and this is more common. I don't know if you've talked a little bit about measuring electricity at all. When you measure voltage, you put your meter parallel or across the component. You don't have to interrupt the circuit. You can measure the voltage. Well, you have to measure voltage while the circuit's operating. To measure current, you have to shut off the circuit, disconnect it, and hook the meter into the circuit. So it's difficult to measure current. So more often when we're calculating power, we don't know the current, but we saw up above that the current was equal to the voltage divided by the resistance. So if we put that into our power formula, we can calculate the power formula as voltage squared over resistance, E squared over R. So find the power consumed by a 2.16 kilo ohm load with a 120 volt voltage drop. So it is the only component on that circuit. It's drawing a full 120 volts. We have voltage. We have resistance. That's going to be this formula here. So the power equals, what goes in for E? 120, and that's going to be squared over, what goes in for R? Perfect, 2,160. Have to turn the kilo ohms into ohms. Now we can just enter this in the calculator the way it appears. Is that what we get? So 120 squared, then just divided by the 2160. Yeah, 6.66666. 7 watts is our power draw. So 6 2/3 watts. Find the power consumed by a 1.5 kilo ohm load drawing 25 milliamps. So now we're going to use the formula that is just current and resistance. P equals I squared R. So what goes in for I? .025, and yes, that's going to be squared. Then for the resistance, 1,500. Perfect. So again, in the calculator, to 0.025, then squared times the 1,500. We get 0.9375 watts. So in your notes, I'm going to have you do this. Find the power consumed by a 3.5 kilo ohm load in a 240 volt circuit. Again, assume that it is the only component on the circuit that's taking all 240 volts. So the 240 goes in for E, and that's going to be squared over 3,500. So 240 squared divided by 3,500. 16.46, we'll call it. Yeah. 457, that'll work. Watts. Any questions on those? All right. So the next part's the part where I can go wild a little bit. So circuits with more than one resistor. There are two different ways to combine resistors in a circuit. One is in series. Oops, I don't know what happened there. So if we have two resistors in series, what series means is that whatever current flows through one must also flow through the other. They're on the same path. So series resistors will have the same current because what flows through one must flow through the other. They will divide the voltage. Using resistors in series is one method that is often used to regulate a voltage if you need a voltage other than what is being produced by your transformer. So if our total resistance is labeled R with a little t there, R sub t, and the first resistor is R sub 1, second resistor is R sub 2. So I'm not going to say the sub, I'm just going to say R1, R2, and RT. The total resistance equals R1 plus R2. Actually, I probably shouldn't be using a battery symbol. Use an AC symbol for our voltage source. If this is 30 ohms and this is 20 ohms, my total resistance is going to be, 30 plus 20 is 50 ohms. Relatively simple to figure out. This can extend to as many resistors in series as we want, as long as they're all on a single path. So the total resistance is R1 plus R2 plus R3 plus as many as we want to keep going. So if I have 4 ohms, 8 ohms, 3 ohms, and 5 ohms, how do I find the total resistance? Add them up. Comes up to 20. There should be a 4 there. There should be 20. Yep. 20 total ohms. So if I have a circuit with 120 volts voltage source, I have 8 ohms, 12 ohms, and 4 ohms. I'm going to start cheating on my own symbol and not put the little legs on it. That's the way I've always done it to make it quicker. Find the current. Well, to find the current, we just need to know the voltage, that's the 120, and the total resistance. RT here is going to be 24. So then what's the formula then to find the current? Yeah, voltage of 120 divided by the resistance of 24, which is 5 amps. If I give you a 240 volt circuit and I give you that this is 300 ohms, this is 60 ohms, and the current flowing is 500 milliamps. How would I find the resistance of R2? Well, I would start out by finding the total resistance. We might say, well, I can't add, one of the resistances missing, I can't add them up. But we can use Ohm's law to find the total resistance. Resistance is voltage divided by current. So, 240 ohms divided by 0.5 amps, 500 milliamps, 0.5 amps gives us 480 total ohms. So now what do these two add up to? You got it. That's 360. There you go. This has to make up the difference. So 480 minus 360. R2 has to be 120 ohms. Questions? Parallel resistors. There are some tricks I'll show you on the calculator that make parallel resistors a lot easier to calculate with. So parallel resistors are on different paths. It's a branch of the path. So where the series resistors split the voltage and had the same current, parallel resistors have the same voltage, they split the current. They don't split it equally, but they do split the current. You've heard the path of least resistance. The smaller resistance is going to get more current because it's easier to flow. The one thing that is a big deal with parallel resistors, total resistance is less than any single resistor. So let's say that this is 60 ohms here, and this is 120 ohms. The smallest resistor there is the 60. The total resistance has to be smaller than 60 because it's going to be easier to flow than it would be if it was just the 60 ohm resistor. R total, now the formula that the book uses, your book uses something like this. How does it put it? Is it RT, R1 times R2 over R1 plus R2? That formula sucks. It only works if you have only two resistors in parallel. If you have more than two resistors in parallel, it really is horrible to use. So a little bit better formula looks like this. 1 over the total resistance equals 1 over R1 plus 1 over R2, the reciprocal of the resistance. Now that doesn't look any better until you realize there's keys on your calculator that make this way easy to calculate. So if I'm using these resistances up here, 1 over my total resistance equals 1 over 60 plus 1 over 120. On your calculator, depending on what you have, you all have a button that is either a 1 over x key or an x to the negative 1 key. Both of those mean the same thing. They are reciprocal key. So what you would do is you would type in the first resistance, the 60, press that reciprocal key, plus the second resistance, the 120, press that reciprocal key, and hit equals. So far that would look like this. 60 reciprocal plus 120 reciprocal, hit equals. Then you hit the reciprocal key again and hit equals. So reciprocal equals 40 ohms. And this works with as many resistors in parallel as you could want. I'm only going to do 4 here because that's all I can keep track of in my head as I do these. So let's make this 60 ohms. Actually, that's not going to work if I do 60, is it? I'll make it 80 ohms. This will be 240 ohms. This one will make 60 ohms, and this one over here is going to be 30 ohms. So I can do this whole big thing. 80 reciprocal plus 240 reciprocal plus 60 reciprocal plus 30 reciprocal equals. So I'll punch that much in. 80 x negative 1 plus 240 x negative 1 plus 60 x negative 1 plus 30 x negative 1, hit equals. Hit the reciprocal key again and equals. 15 ohms is my total resistance. Now, if you're using your cell phone, most of your cell phones they do have a reciprocal key, and if you turn it sideways, you get the scientific notation. Some of them, it works a little weird. So if you have any problems with your cell phone calculator working, let me know. We'll take a look at it. Yeah, that one little key saves a lot of work on those formulas. That one has it. Yep. So yours will be right about the center. On the cell phones, it's a little tougher to find.
Double check. Yeah, you get the same problem on this cell phone too.
So yeah, on the cell phone, when you turn it sideways, it's usually a 1/x key. Yeah, that's the 1/x key right there. So you have to hit the 1/x key first and then type in the number. So once you get to that answer, you have to write down the answer, hit the 1/x and type it in. Anybody else have a different one that they're trying to find?
There was probably like 4 weeks of baby training.
Really?
Yeah, because
I don't mean to laugh at you, but
like they had us do it on a computer, and
oh sure.
doing it on a computer was the basic computer calculator. Nobody told us that. I guarantee you, it's thousands of people, thousands of hours.
Oh sure.
I'm more annoyed by that.
So if we talk about combination circuits, most circuits are a combination of series resistors and parallel resistors. Part of the trick is breaking down the circuit, redrawing it in such a way that we get the resistors where we can break them, where we can identify how they're related. So let's put 30 ohms here. We'll do 40 and 40. For me, it's always easier if I redraw the circuit with all the resistors going down the right side. So my voltage source is on the left side like this. And all my resistors are going to go down over here on this right side. And to do that, I just start at my voltage source and I start traveling around my circuit clockwise. The first thing I run into is this resistor here. So coming down, I have that resistor, 30 ohms. Then I hit a branch where it splits off. So I split it off. One side of the branch is the 40 ohms. I'll put that over here. The other side of the branch is also 40 ohms. So I'll put 40 ohms over here. Then it comes back together. So it comes back together, and that's all of my resistors. Having it drawn like this, at least for me, makes it easier to combine. I start out, if there are anything that's just in simple series next to each other that I can add, I don't have that here. Is there anything that's in simple parallel that I can combine? Yeah, these two are in parallel, right? So how do I add them together? I do 40 reciprocal plus 40 reciprocal equals reciprocal equals is 20 ohms. So what I'm going to do is I'm going to replace these two with a single 20 ohm equivalent resistor. So it's called an resistive equivalence. Those two resistors in parallel are the same as a single 20 ohm resistor. Now what is left is just that equivalent resistor and the 30 ohm resistor, and are they in series or parallel? They're series. So how do I combine them? I simply add them. 30 plus 20 gives me 50 ohms. That is my total resistance. So the trick is getting the circuit redrawn in such a way that we can break it down. So we might look at one a little bit more, I'll stay somewhat simple yet. Come on. That's horrible. That's good enough. We're short on time. So here, this is obviously a combination of resistors in series and parallel. So once again, I'm going to draw it with my voltage source on the left. We hit a branch here, so we're going to branch them off. One branch has two resistors on it, the 75 ohm and the 25 ohm. The other branch also has two resistors, the 200 ohm and the 100 ohm. And then they come back together, and then that goes back to the voltage source. Here, again, the first thing I look for is resistors that are in a simple series relationship. 75 and 25 are in series. I combine them to get what? 100 ohms. So what I'm going to do is I'm going to replace that with a single 100 ohm resistor across there. The 100 and 200 are in series. I'm going to replace them with a simple what? 300. I just add them together. Come on. So now all that's left are the 100 and the 300 equivalent resistors. They are in parallel. So it's 100 reciprocal plus 300 reciprocal equals reciprocal and equals. We get 75 ohms is our equivalent resistance. So the total resistance there is 75 ohms. So in this circuit, since we have it up, let's find total current. I total, IT. The total current is found using Ohm's law. We have the total resistance here. We have the total voltage. So the current is just the voltage of 24 volts divided by 75 ohms, which is going to be 320 milliamps. 0.32 or 320 milliamps. So this is the total current right here. 320 milliamps. Now, if I want to know the current in each resistor, remember we said the voltage stays the same. So the voltage across this branch is how much? 24 volts. It's the full voltage. So I have 24 volts across an equivalent resistance of 100 ohms. So we do the 24 volts divided by 100 ohms gives us 0.24, right? This is going to be 240 milliamps across here. Perfect. Yeah, this is going to be also 24 volts across the 300 ohm equivalent. So 24 over 300 is going to be 0.080. That's 80 milliamps. And yes, it's called Kirchhoff's laws, as there's called a joint law. 320 milliamps coming into this joint, 240 and 80 is 320 milliamps coming out of that joint, so that they add up. Yes. Well, since we're having fun, sure. Let's do the voltage drop across each resistor. The voltage is current times resistance. So the voltage drop on that resistor is 0.240, that's the 240 milliamps, times the 75 ohm resistor is going to be what? Is that 18 volts? 18 volts there is that voltage drop. Now we know there's 24 volts across this whole branch, so the bottom one has to be 6 volts. We could do the 25 ohms times 240 milliamps is going to give us that 6 volts. Over here, we still have 24 volts across this. We have the 80 milliamps there. The voltage drop there will be 0.08 for the 80 milliamps times, we'll do this one first, 200 is going to be 16 volts. Which means the bottom one has to be 8 volts. If we did the 0.80 times the 100, we would get the 8 volts. Power consumed. Power is voltage times current. So for this one, I'm running out of colors here. 18 volts times 240 milliamps. That's 18 times 0.24. Gives us 4.32 watts there. This is 6 volts times 0.24 is going to give us 1.44, I believe. Yeah, 1.44 watts here. Over here we have 16 volts, 80. So that's 16 times 0.08, which is going to be 1.28, is it? Yeah, 1.28 watts. This will be 8 volts times 0.08, which is going to be 0.64 watts. Now, if we add all of those up, it'll give us the total power, 7.68 watts. We can double check. We had 24 volts and 320 milliamps, so 24 times 0.320. I can't write for some reason. This is a 7.68. They come out to be the same. Okay, we are at that time, so I got to give you a worksheet and then let you guys get out of here for lunch.